So we've been looking at a variety of different forces recently involving gravity. So we're going to look at a couple more scenarios and stuff, like get a little more practice in with some of the forces that we've been looking at, and do a little more practice and stuff like that. So we're going to, they're all going to involve gravity in some way, but we are going to start with another super classic scenario, and that's an elevator type question. And just going to draw an elevator. So there's the cable coming down to the elevator, and oops, change the color so the inside. All right, so another really common scenario for gravity type stuff is a person standing in an elevator. So got a person standing in the elevator, and let's say this person is, let's say they are they're 64 kilograms. Okay, now when you're standing in an elevator, when the elevator moves up and down, you feel different things. And of course, that actually connects to something else we were working on that connects to the normal force. The normal force, that's what you feel in your feet. You actually feel the normal force in your feet. And depending if the elevator is, moving up or down, accelerating, slowing down, all that kind of stuff, you feel different amounts of pressure in your feet. So let's take this guy right here, take this little situation right here, and let's say he's feeling a normal force in his feet, and let's say he's feeling 800 newtons of normal force between his feet and the elevator. Now this actually tells you something about the elevator, because if you are in an elevator, the amount of normal force you feel actually helps to tell you which way the elevator is actually going. So I'm just going to start with something basic. I'm going to find the weight of the guy. If I'm just going to find the mg for the guy using his mass. And if I do that, I get like a 628 newtons. So that is his weight. Now this helps me out, because if the guy was just standing in the elevator and the elevator wasn't moving, the normal force that he would feel on his feet would just be 628. But he's not feeling 628. He's feeling 800. He's feeling more force on his feet than usual, and that tells you that the elevator must be accelerating upwards. It has to be going up, because when elevators take off and start moving, you feel more pressure in your feet when it's lifting you up. So that tells me that the elevator is actually moving upwards. So he's got that 800 newtons of normal force on his feet. Now, part of that force, 628 of that, that's just to balance off the force of gravity. So the floor of the elevator has to push up with 628 just to balance off gravity. But it's not just pushing with 628. It's actually pushing with more than that. It's pushing with an additional 172. It's also pushing with 172 newtons in order to accelerate. So there's 800 newtons of normal force on the guy's feet. 628 is just to balance off gravity, plus an additional 172 to actually accelerate them upwards. So this would be the net force. This is very similar to the rope type thing, hanging on a rope type question, tension on a rope, same idea. Okay. So if that's my net force, I can use that to find out the acceleration of the guy. So let's take that net force, I'll take that 172 and divide that by the 64, and I can get the acceleration. So I'll do the 172 divided by the 64, which leaves me with around 2.7 meters per second squared, and I already know that he's accelerating upwards. Okay, so that's how we can figure it out. And of course, if the elevator was accelerating down, you'd feel less pressure on your feet. You feel less normal force. Now, another way you could actually do this, and this is another really common way people do it, is they will just take that 800 newtons right there. They'll just take that 800 newtons and divide that by the 64 kilograms. And if you do that 800 divided by 64, you will get 12.5 meters per second squared, which is sort of the total acceleration acting on the person. The only thing is, part of that, 9.81 of that, is for gravity. So what you'd be left with is about 2.7 meters per second squared in order to accelerate. So it's the exact same idea, the exact same concept. except some people look at and sort of like, adding, subtracting the forces, they'll look at adding and subtracting the accelerations, but it doesn't make any difference. You'll end up with the same type of thing, okay? Now, we could do like a similar type of scenario. What if we just adjust this a little bit, okay? And we said that he's accelerating downwards at 1.6 meters per second squared. So what would the Fn be now? Okay, well, let's just start with basic forces. Now, there's a couple ways you can do this again. It doesn't matter. But the force of gravity, my mg, is 628. Okay, so that force doesn't change. But I've got the acceleration. So if I do the F equals ma for that, if I do the F equals ma, where I take the mass of the guy, I take the 64, and I times that by the acceleration of 1.6, I get about 102 newtons. Okay, so it's very similar to what we were doing up there. Okay, so the force of gravity is 628, and if the elevator was just sitting there, the normal force would be 628. That's it. But it's not just sitting there, it's accelerating downwards. And since it's accelerating downwards, he's going to feel less normal force, less pressure on his feet. Well, how much less? Well, apparently 102 less, because that force is being used to accelerate them. So all we have to do is take these two and subtract them, and we would be left with about 526 newtons, and that would be the Fn. So you're standing in the elevator, your weight would be 628. You're still going to feel 526 newtons on your feet because you're losing 102 going towards the acceleration of accelerating you down. Okay, so very similar, just, if you feel more pressure, you can add the forces. If you feel less pressure, less normal force, you can subtract the forces. Okay, and the same thing applies to if this guy was, same thing as like when the tension of the rope type question. If the elevator was moving at a constant speed, then the Fn would just be the mg because there's no extra acceleration. Moving at a constant speed, whether it's constant speed up, constant speed down, the mg would just be your Fn. It would just be the same. Okay, and when you guys have been in elevators before, the elevator starts moving up, you feel more pressure in your feet, and then it backs off. Then you feel relatively normal, aside from the vibration. Same thing for going down. You feel normal, the elevator starts going down, you feel lighter for a second, but then as it's going down, you feel relatively the same because there's no extra acceleration, so Fn would just be equal to your mg. Okay, so there's a little more practice with mg, a little more practice with normal force, and the elevator is a super common basic way to practice normal force calculations. Okay, so normal force also connected into some friction type stuff. We started looking at some friction stuff as well. So I am going to, let's do a question with some friction and sort of do some friction calculations and incorporate Fn into that as well. Okay, so let's just look at a basic situation of friction. Here we need to get let's get a surface going here. So there we go, surface, and let's just do something super classic and simple. It's basic box, something like that. Here, let's color in the box. There we go. Just draw a guy pushing on it, something like this. All right. Oh, he's all grumpy, broken knee. Okay. So, guy pushing on box, we're going to do pretty standard situation type, friction type question, no big deal. Okay, so let's say we've got a 40 kilogram box and the guy is pushing on the box, and where the coefficient of friction, is sort of how well two materials sort of slide against each other. And let's say the coefficient is going to be, let's just do 0.20. Okay, it's often like around a decimal, around 1 or 2. It's relatively common. When you get things like 8, 9, 10, like that's crazy high coefficients of friction. So he's pushing the 40 kilogram box, pushing with there's a coefficient of friction of 0.2 between the box and the ground. And let's say he is pushing, of course, my applied force, my Fa. Let's say that he is pushing with, let's just go with 300 newtons. Okay, and let's just start really classic. What's the acceleration of the box? Okay, so this is where I like to ask myself, what's trying to move it, what's trying to slow it down, that type of thing. So if I just go with what is trying to move the box, the only thing actually trying to move the box is the applied force of 300. So I've got 300 newtons trying to move the box. Okay, anything else? No, that's it. All right, so what's trying to slow down the box? Okay, well, obviously there's friction is trying to slow down the box. And if you remember the expression we had for friction, friction is mu Fn. So I need to find my Fn. And of course, in this circumstance, the Fn is between the box and the ground, and the Fn is because of the weight of the box. So if I find the mg for my box, this will give me my Fn. That's why it's really common to actually see friction written as mu mg. Mu mg is not actually the formula for friction. It's like a specialized circumstance where it's just, the normal force is just the weight of an object, and then you just sort of put it in there. So it's really common to see mu mg, although technically the formula for friction is mu Fn. Fn is often equal to mg, so whatever. So if we calculate that out, we've got the mu, we've got the everything we need, we can actually punch out how much friction we have. And when I punched out, I get about 78 newtons. And technically it'd be a negative force because of slowing it down, that type of thing. Okay, I'm not gonna worry about that too much. So there's my force trying to move it, and there's my force trying to slow it down. There's no other forces involved. So now I just gotta put those two together, and that will give me my net force. So if I calculate my net force, all I'm gonna do is take my 300 and subtract my 78, which leaves me with 222 newtons of force. And that would be the force for the acceleration, because acceleration, F equals ma, you typically are using net force. So once I have my net force, my acceleration would just be the F net divided by the mass. I'll just take that 222 that I had left over, divide that by the mass of 40, and I will get an acceleration about 5.6 meters per second squared. And that's it, and that's how you incorporate friction. Okay, so let's modify this a little bit. Let's change this up a little bit. Let's have him go, and maybe the ground gets all like bumpy and jaggedy and that type of stuff over here. It gets all rough over here. So he's going to hit that rough patch over there. And because of that, over here, there's going to be a higher coefficient of friction. It's all bumpy and rough and stuff like that. So let's find out what that new coefficient of friction is if when he gets there, there's no more acceleration. Okay, so let's take the exact same setup, whatever you want to call it. Okay, so let's say this guy hits a really, really rough area. Okay, and the acceleration goes to 0. So it's not accelerating at all, just constant speed. What is the, what's the new, oops, not y, what's the new coefficient of friction that is over there? So what's the new coefficient of friction? Now this actually brings up like a special type of a situation where we don't have any acceleration. This is a special situation that's called equilibrium. Now equilibrium, the core word of equilibrium, of course, is equal. And it's called equilibrium because all the forces are equal to each other. And that basically means that the net force is equal to 0, which means you have no acceleration. So there's two kinds of equilibrium. There is dynamic equilibrium, so dynamic equilibrium, and there's also static equilibrium. And both of them have a net force equal to 0. That doesn't change. But with dynamic equilibrium, this is when you are moving, and static is when you are at rest. So dynamic equilibrium would be something moving with a constant speed, but the net force is 0, so there's no acceleration. For example, like a car with cruise control on the highway is in dynamic equilibrium. Where static equilibrium, you're just at rest, sitting there, not accelerating, not doing anything. So this box, for what we're talking about here, this box would be in dynamic equilibrium because it's hitting the rough area, he's still moving, and the acceleration is 0. So the big key part for equilibrium is that whole F net is equal to 0 type thing. So I know the net force on the box is 0. So if I try my other, the same type of thing I was talking about before, how much is trying to move the box? Well, 300 newtons is trying to move the box. And then I ask myself, how much is trying to slow it down? Well, I don't know because I can't find new friction, but I do know that my net force is equal to 0. Well, if I've got 300 trying to move it, and the net force is 0, that tells me that there must be 300 newtons trying to slow it down. Friction must now be 300 newtons to cancel off the applied force of 300 newtons. So this helps me out to figure out what friction is. So this must be my new force of friction. Okay, so if I wanted to find the coefficient of friction, if I go back to the basic expression for that, the coefficient of friction is FF over Fn. Well, my friction I now know is 300 newtons, so it's canceling off the 300 that's trying to move it. So I know that's 300. So this is my 300 up here. And my FN has never changed. My FN has always been the same. My FN is still going to be the mg for my box, which is the 40 times the 9.81. So, and that was, oh, there's the FN right there. And if we sort of punched out that mg for this is actually 392 newtons. So that's the weight. The weight of the, you didn't actually have that written down anywhere. That's 392 up there. That's the actual weight of the box, which is also our N. So this is going to be 392 right there. So I'll just take the 300 and divide it by the 392, and I will have my new coefficient of friction. So it's just the 300 divided by 392, and we're looking around 0.77. Now there's no units because it's a force divided by force, so the units actually cancel out. There are no units. It's just a ratio of the two forces. So our initial coefficient was 0.2. That's what we had at the beginning of the question. And then hit the rougher area where there's a higher coefficient of friction, and that gives us a coefficient of 0.77. And of course, the equilibrium thing, you know, when you see equilibrium, forces are canceling out, you know the net force is 0, the acceleration is 0. The speed or velocity doesn't have to be 0, but both the acceleration and the net force will be equal to 0 because that's what equilibrium does. Okay, all right, so let's clean this up and let's look at another basic friction type question. Okay, so let's look at another situation here, similar to what you guys done before, with a table of some kind. Fill that in. You know, the old table and pulley type setup, something like this. Over there. Okay. Actually, let's move this down a little bit. There we go. That's a little better. All right, so put a couple boxes on here. Done this type of thing before. Oops. All right, so there's a box there. Let's use the, oops, no, it doesn't matter. And let's put another one down here. It's red, there we go. Okay, oh, red. Okay, so put some cables on here. All right, so very similar to what you guys have done previously. We're just going to adjust it and incorporate a little bit of friction into here. See what we can do. So I've got a couple boxes. Let's say this box up here is, let's say 7.2 kilograms. And let's say this one here is 5.8 kilograms. And we're going to see what we can do here. Now, I know that my gravity is going to be important, so I'm just going to find my mg's to begin with. And that's a really common thing. Like, if you got masses and you know it's going to probably be involved, why not get the mg's out of the way so you have them? So even if you don't know what they're going to do or how they'll be, you know, incorporated, that doesn't mean you can't find them. And I'm going to find them for my two boxes. I got the 71 newtons is the mg for that one over there, and then I'll find it for the little red box down here, which is find the mg for that. 57 newtons there. And again, like sometimes just find the mg's. Even if you don't know what to do, it's just one little piece that you can find that you don't have to do later on, or you can link together with other stuff. Okay, so I've got the 71 newtons, I've got the 57 newtons, I got my two weights. We're all good to go. Okay, so let's take the situation and let's try this. It is in, let's say this is in static equilibrium, so it's not going anywhere. It's totally at rest. Now, if it's at rest, I know that the acceleration is 0, forces are canceling out, all that kind of stuff. So what I want to know is what is the coefficient of friction between the table and the blue box? Because I know it's in static equilibrium. So I'm going to ask myself the same type of questions I usually do. How much is trying to move it? Well, the red box is the one trying to accelerate the system. So if I cut the rope, that's the one that would fall. So I've got 57 newtons is trying to move it. Okay, nothing else is trying to pull it. So 57 is trying to move it. So let me ask this, how much is trying to slow it down? Well, if this thing is in static equilibrium, this tells me that my net force has to be equal to 0. All the forces cancel out. So I've got the applied force, and let's sort of what this one is. That's my applied force right there, that 57. I've got an applied force of 57 newtons trying to pull it down. But if it's not actually going anywhere, that tells me I must have 57 newtons trying to slow it down to cancel out the applied force of 57, and this must be my force of friction. That would be between the blue box and the table. So now I know my force of friction because we're in a static equilibrium. So if I use that idea, coefficient of friction is FF over Fn. Okay, now I figured out my force of friction's got to be 57 to cancel out the applied force of 57. My Fn, well, that would actually be this right there. That'd be my 71 because it's the blue box that actually has the normal force and is causing the friction. So I'm going to use that 71. And all I then have to do is divide the 57 by the 71, and I got a coefficient of friction of about 0.80. So that coefficient of friction will be required in order to cause the thing to perfectly just not move. All right. If the coefficient of friction is any lower than that, this thing is going to start accelerating. If it is higher than that, it still just isn't going to go anywhere. All right, so let's modify this again so we can do some more stuff. Let's take that coefficient of friction, let's reduce it. So let's reduce the coefficient of friction. We'll see there. Reduce the coefficient of friction to 0.65. So now what would the acceleration be? Okay, so I know it's going to move. All right, so I'm going to ask myself the same questions I typically do. How much is trying to move it? Well, for me, that's still that 57 newtons. That hasn't changed at all. Slow it down, of course, that's my friction. So force of friction is going to be mu Fn, and it's still the same Fn as before. The only thing that's changed is my coefficient of friction. So I do that 0.65 times the 71, and my force of friction is now going to be around 46 newtons. And of course, it's going to oppose the motion. So you can put negative in front if you want to. I'm not too worried about that right now. So let's piece things together. I've got 57 trying to move it. I've got 46 trying to slow it down. So I'm just going to subtract the two, and then my net force would just be the difference, which would be 11 newtons. 57 take away 46 is 11 newtons. So I've got 11 newtons of net force. And now that I have that, acceleration, of course, is just net force divided by mass. And of course, remember, the two are tied together. You want to use the total mass altogether. So I've got that 11 newtons of net force divided by the total mass of 13 kilograms. And I will get an acceleration of 0.85 meters per second squared. And obviously, it's sort of like going towards the right, I guess, something like that. Okay, so there's some more practice with basic friction and normal force for both an elevator type, classic type question, and then a couple basic box questions. Okay, so let's do one more question here, practicing with the coefficient of friction, that type of thing. And let's see if we can incorporate some kinematics into it as well. Okay, so let's draw some grass or something like that. And we'll draw something like this. There we go. Big spider. There we go. There we go. We'll get some more webbing stuff in there. All right, so we got a spider with dragging a person along that they've captured. Okay, moving along, and let's get some quantities into here. So suppose he's got a 45 kilogram human snack, and he's pulling him along, and he's going to start at rest over here. Okay, and let's say they're moving along, and let's say that they go a certain distance, and of course they're going to accelerate as they go. So let's suppose that the spider drags the person, and let's say it goes 7.5 meters, and it takes approximately, well, let's go with around 12 seconds. So it goes 7.5 meters in 12 seconds, starting at rest. Okay. And let's say the spider here is pushing or pulling, yes, with 50 newtons of spider force. Okay, so starts at rest, pulls with 50 newtons, goes 7.5 meters in 12 seconds, and the guy's 45 kilograms being dragged across the ground. So what is the coefficient of friction between the person and the ground? Okay, well, let's just find a few things here, start with some basics, and see what we can do. We got mass. You know what? I got mass. You know what? I'm going to find my mg for the guy because that's going to come in handy, and that gives me about 441 newtons. That's his mg, and this will also be the Fn for him and the ground. I get the applied force, so I got an applied force of 50 newtons right there, and I got some kinematics. I got some distance and time. Well, I'm going to work with my distance and time stuff a little bit. And if I do my distance and time stuff, distance and time, of course, give me speed. More specifically, they give me average speed. So if I do that, if I do the 7.5 divided by 12, I get an average speed of 0.625 meters per second. And since he started at rest, if the average speed was 0.625, that tells me my change in V must be 1.25 meters per second squared. Started at 0, went up to 1.25, so the average is going to be 0.625. So I had to double it, started at 0. All right, so I got my delta V. Well, again, more basic kinematics. I've got my change in V, and I've got my time. I can find my acceleration. So if I take that 1.25 divided by the 12 seconds, I've got an acceleration of 0.10, I'll include the 4, meters per second squared. So I've got an acceleration of just over 0.1. All right, there's just kinematics type stuff. All right, and I've got my acceleration, which means now I can connect it to my dynamics type stuff. Okay, got my acceleration. I do have some mass. Well, I've got acceleration, I've got mass. Acceleration and mass give me net force. So I can calculate my net force. Net force is equal to ma. So I'll take that acceleration of 0.104 and times it by the 45, and I get a net force of about 4.7 newtons. Okay, so let's see what's going on here. How much, and this is going to go back to my basic questions, how much is trying to move it? Well, that's 50 newtons. That's my applied force. 50 newtons is trying to move it. How much is trying to slow it down? I don't know. I don't know my friction because I don't know my coefficient. But I do know I'm getting like 4.7 newtons. I know my net force is 4.7 newtons. So the spider's pulling with 50, but it's only getting like 4.7. I must be losing the difference between the two. I must be losing 45.3 newtons to friction. So pulling with 50, losing 45.3 to friction, and that leaves me with a net force of 4.7. So now that I have my force of friction, let's see if I can find my coefficient of friction, because coefficient of friction is FF over Fn. So let's see. FF, yep, I figured that out. My Fn is just the mg for the guy. So I got everything that I need. So I'll just take that 45 and change, the 45.3, divide that by the 441, and I get a coefficient of about 0.10 between the guy and the ground. Okay, so there's just some basic friction dynamic stuff and incorporated a little bit of your kinematics as well. So again, often it's really common. Use some kinematics to get the acceleration, which then leads to forces, or often use forces to find the acceleration, which can then lead into some kinematics.